Assalamualaikum warahmatullahi wabarakatuh. My name is QAWIEM bin AMIRNUDIN from class CEE 2224B. So, we are a group of students from class CEE 224B and this is our video presentation for MAT575 Assessment 2 titled Curve Fitting for Real World Data. For this project, we conducted an analysis of the relationship between screen time and sleep duration using a various curve fitting techniques, including linear, quadratic, and a text-selected model. The dataset used was obtained from Kaggle, specifically the Student Mental Health Analysis dataset. From this dataset, we selected a sample of 10 students, each with recorded values for their daily screen time and average sleep duration. The objective of our project is to determine the most appropriate curve fitting model that accurately represents how screen time may affect sleep duration. Scatter plot. This scatter plot displays the data we use. The x-axis represents screen time in hours per day, while the y-axis represents sleep duration in hours per night. Visually, the point suggests there may be a relationship between these two variables. Our goal is to find a mathematical model that best describes this relationship. We begin our analysis with the linear least square method. The first model we apply is the linear least square model. This model assumes a straight line relationship between the two variables and takes the form fx is equal a0 plus a1x. To find the values of a0 and a1, we use the normal equation written in the matrix form. Based on our dataset, we have the following values. If we look at the table, we have already sum of number, sum of x, sum of x squared, sum of y, and sum of xy. By substituting this value into the matrix equation, we will solving the system. We will obtain the following coefficient. A0 is equal 5.1376 and A1 is equal to 0.1811. Therefore, the equation of the best fitting line is fx is equal 5.1376 plus 0.1811x. This means that for every additional hours of screen time, the predicted sleep duration increases by approximately 0.18 hours according to this model. We then plotted this linear equation over the scatter plot to visualize the fit. While the line shows a general upward trend, the accuracy of the model will be evaluated further using the sum of squared error, which we will compare with the other model later.
Assalamualaikum warahmatullahi wabarakatuh. My name is AZWANA MADINA binti MUHAMAD. So today I'll be presenting a comparison between two least square models. The first one is the quadratic least model and another one based on the exponential functions. So let's restart with the quadratic model, which has the general form fx equal to a0 plus a1x plus a2x squared. By using the normal equation as shown, we set up and solve the system by using the matrix as shown here. By solving the matrix, it gives us the coefficient a0 equal to 1.6332, a1 equal to 1.4731, and a2 equal to negative 0.0987. By getting the coefficients, the final model is function equal to 1.6332 plus 1.4731x minus 0.0987 x power of 2. So here the graph of the quadratic fit. As we can see, the curve fits the trend of the data quite well, capturing the rise and fall pattern of the data points. The other model that we use is exponential model. We apply the exponential model defined as y equal to a exponential power of bx. Taking the logarithm, ln y equal to ln a plus bx equal to y equal to a0 plus a1x. This converts the exponential problem into a linear least square problem. To solve the system is by using the matrix as shown here. From the matrix, we can get the a0 equal to 5.1376 and a1 equal to 0.1811. Taking the exponential of a0, we can find the A. A equal to exponential power of 5.1376 equal to 170.3. So the final model is function equal to 170.3 exponential power of 0.1811x. So here is the exponential fit. As we can see, this model does not capture the curved nature of the data well. It's increasing while the actual data peaks and then decreases.
I'll be giving an overview of our study on the relationship between screen time and sleep duration using 3 regression models. Firstly, we started by applying the linear model, which assumes a straight line relationship. The equation showed that sleep increases slightly with more screen time. While this model was simple and easy to understand, it didn't handle changes in the trend very well. Its sums of square error or SSE was 21.3, which showed moderate accuracy. Next, we use the quadratic model, which adds square terms. This allowed the model to capture a curve in the data. It showed that sleep increases with time up to a certain point, but then it begins to decrease. This matched real-life behavior more closely. The quadratic model had the lowest SSE of 18.32, meaning it was the most accurate of these three. Finally, we tested the exponential model, which assumed that sleep grows rapidly as screen time increases. This model predicted unrealistically high sleep values, especially at higher screen time, and had a very large SSE of over 406,000, making it least reliable. So we can say that the quadratic model gave us the best fit. It's not only reduced prediction error, but also reflected a more realistic pattern seen in behavioral studies, where moderate screen time may be okay, but too much can harm sleep.
Hi, Assalamualaikum. My name is Sheikh HAZIM, and I'm going to present the model correlation and justifications by using the SSE. So as you can see, there are 3 models, which is linear model, quadratic model, and also other model, which is the exponentials. So for the linear model, based on the plot, draws a straight line through the data, and what it does, it captures the general trend. So more screen time means less sleep. So and also it doesn't quite follow the shape of the data, if you can see based on the plot graph. And for the SSE, shows that the model has a fair amount of error. So it's good, but still not the best lah. So for the next one, which is the quadratic model, this model adds a bit of curve to the line, which help it fits the data more accurately. So the SSE also lower than the linear model, so it clearly follows the charges in sleep more closely. So especially where the relationship might not be a simple straight line. And for overall, it give a better picture of this trend lah. And for the last one, which is the other model, exponential, was meant to capture a more complex, possibly a curved trend, but in this case, it performs very poorly. So this is because the SSE is extremely high, which tell us that the predictions were way off. It's likely the model didn't match the pattern in the data at all and may have overcomplicated things, especially given the small sample size.
To analyze our data, we applied 3 types of models using the least square fitting method, linear, quadratic and exponential. Starting with the linear least square model, the equation we used was fx is equal to 5.1376 plus 0.1811x. We derive the slope and intercept by minimizing the sum of square errors, which we will call it as SSE. This involves calculating terms like x squared and xy to form a system of linear equations. Next, we move on to the quadratic model, which has the form of fx is equals to 1.6322 plus 1.4731x minus 0.0987x squared. This model includes higher order terms such as x squared, x cubed and x to the power 4, allowing it to capture the curvature in the data that the linear model missed. We determine the coefficients by solving a more complex system by using partial derivative of the SSE. Next, we tested an exponential model, which is fx is equal to 172.8113 exponential 0.0271x. We first linearized the model by taking the natural logarithm of the y values, then applied the least square method. Here comes the part where we face some challenge. So, one of the main challenges was selecting the right model. The linear model was easy to interpret and compute, but lacked the flexibility to follow the curvature in the data. The quadratic model, while more accurate, introduced complexity in both computation and interpretation. It's not always obvious when a quadratic model is appropriate unless there's a theoretical reason. The exponential model highlighted another issue: overfitting and instability. Its parameter caused it to produce extremely large outputs for high x values, which led to a huge sum of error. This shows us how sensitive exponential can be if the data doesn't match that kind of growth. We also dealt with limited data points, that is only 10 data points. With such a small data set, only outlier could influence the fitting process significantly. For example, the point at 7.1 and 8.9 impacted the linear model slope more than others. And then lastly, we considered interpretability. Even though the quadratic model fit best statistically, it might be harder to justify if we don't expect a squared relationship between variables in the real-world content.
To wrap up this study, we aim to find which regression model best explains the connection between screen time and sleep duration. After testing linear, quadratic, and exponential model, we found that not all fits the data equally well. The quadratic model stood out. It captured a more realistic pattern where sleep increases with screen time only up to a point, then began to decline. This model gave us the most accurate result with the lowest error score, showing it the best to represent how screen habits may affect sleeps. The linear model, while simple, didn't handle the change in direction very well, and the exponential model gave unrealistic predictions, especially with high screen time. It assumed sleep would just keep increasing, which we know isn't true. Looking ahead, we recommend testing other models like cubic or logistic regression to see if they can better capture more complex pattern. Also, analyzing things like residual would help confirm how good the models really are. And also collecting more diverse data like from different age groups or screen time situation could improve how well the model work in real life. In short, while this study found that a quadratic model worked best for now, there's room to grow by using deeper analysis and broader data in future research.